In this video, let's pick up where we left off in class, where we were talking about improper integrals, starting with type 1. So recall that a type 1 improper integral is an integral which includes a boundary or a limit of integration of either infinity or minus infinity. And of course, this is improper because you can't actually integrate all the way to infinity. It's not a number, it's not a position. But it's kind of the idea of, well, if we could continue, say, from example, from 1 to infinity, finding the area underneath the curve from 1 all the way forever, what would happen? And, essentially with the type 1 integral, improper integral, we need to, as I call it, extract the infinity in the form of a limit. Since we can't actually plug in infinity, we could instead evaluate what happens to the pattern of the generalized integral as it approaches t, which is continuous and is well defined, and we could evaluate using the fundamental theorem. And then after we figure out the pattern of what the antiderivative looks like, then we can take the limit as t approaches infinity to figure out what happens. Like in the case of this particular integral, the one we did in class, if we examine the pattern of what happens as we integrate all the way from 1 going on forever, and what we saw is what that amounted to be must have been a finite amount, and the limit of that approached 1, because as we integrated to 10, I believe we got 9/10, and as we got, as we generalized the integral to t, what we saw is, well, it maxes out at 1, and then subtracting 1 over t just based on the pattern of the antiderivative. And of course, as t approaches infinity, this expression approaches 0, leaving us with 1. And and just once again, we say that improper integral type 1 that has a finite solution is called convergent. So we say that this area converges even though it is an infinite segment. It doesn't an infinite amount of area, or not. It's not an infinite amount because what we see is it's bounded above by 1, but it does go on forever is kind of what I'm saying, which again can seem very paradoxical. And we did another example of an integral which went to infinity, which was also finite. So let's do another example because they don't always converge. And what's interesting is very similar looking functions may not converge. So again, if we wanted to determine this next example from our packet, again, we could, as I like to say, extract the infinity in the form of a limit. So what I'm going to write is the limit as t approaches infinity of the integral as 1 from 1 to t of our function. Now that we've done so, we can integrate our function by the fundamental theorem of calculus. And as we know, the antiderivative of 1 over x is the natural log of the absolute value of x. And so that would be evaluated from 1 to t. And now plugging in the boundaries of integration, what we would get is the limit as t approaches infinity of the natural log of the absolute value of t minus the natural log of 1. Which is, of course, 0, because log of any base of 1 is always 0. And so what this leaves us with is the limit as t approaches infinity of the natural log function. And as you probably remember, it is an unbounded function where if you plug in larger and larger numbers, there is no limit on how large a natural log can get. So what this gives us is infinity. And this is an example which we say that the area of the integral, or the answer to this region, diverges, or it's a divergent amount. And kind of imagining the graph of what we're examining here. So the reciprocal function is a nice symmetric function with respect to a 45-degree linear function y equal x. But, if we're integrating from 1 to infinity, essentially what we'd be looking at is the area under the curve going all the way forever. And basically what we've concluded is that is not a finite amount, that it has no bound. As you keep going and going, there's no limit to what area you would obtain. And of course we can see that because the area under the curve is modeled by the natural log, which is unlimited. Whereas the previous function, the antiderivative, was modeled by 1 over t, which is limited as t approaches infinity. But again, I wanted to point out there's not a huge significant difference between these two examples, 1 over x squared, which is like the reciprocal square function, which has a vertical asymptote and a horizontal asymptote at 0 and kind of approaches 0 relatively rapidly. Well, the reciprocal function also heads to 0 pretty rapidly, just not quite as rapidly. And so it's interesting to point out that there sometimes is a fine line between integrals to infinity converging and diverging, where we can see just a simple difference between x and x squared in the denominator can be a very vastly different answer at the end of the day. So let's go ahead and just do one more example, and to sort of develop a rote skill for doing these integrals. Again, we can follow the same procedure where I'm going to take out the infinity as a limit. Again, t being completely arbitrary. And 1 over x cubed I could rewrite as x to the minus 3 and use the power rule to solve the antiderivative if I didn't already have it memorized. And again, after pulling out the limit, we want to first solve the integral because we have no idea what this limit is until after we simplify and solve the integral. But the antiderivative of x to the minus 3, by power rule, we would add 1 to the exponent, which would be x to the minus 2, and we would drop the reciprocal. So we get negative 1/2. So from negative 1/2 x to the minus 2, which is the same as dividing by x squared from t to 4. And now plugging in our boundaries into the antiderivative by the fundamental theorem, this would leave us with negative 1 over 2t squared plus 1 over 2 times 16 would be 1 over 32. And similarly, because as t goes to infinity, whether it's 1 over t, 2 over t, or 2 over t squared, if we ever have a division by a variable, the limit, as you divide it, if you plug in a larger and larger number into the denominator, it becomes smaller and smaller. So similarly, this limit here, now that we've evaluated the integral, we can solve the limit. And whatever that limit, whatever our conclusion is from the limit, is the same conclusion about whether this area converges or diverges. So what I would get from this is 1 over 32. And again, I would conclude that this integral converges.